Good morning, good afternoon, and good evening, everyone. My name is Ina Paricio. I am a marketing manager here at EDB, and I will be your host today for our webinar, Graph Queries with PostgreSQL. I am joined today by Simon Riggs, who is a Postgres fellow at EDB, and I am very thankful to have him on the call today as he has not been feeling 100% for the last few days. And before I turn it over to Simon, I just want to go a few housekeeping items. Number one, this presentation is being recorded. So we will be sharing the recording and the slides after the webinar via email. Lines are currently muted. So if you have any question, just drop it in the question panel and we'll go over it. If by any reason we're not able to go through all the questions today, we'll make sure to follow up afterwards. And now with that said, I will hand it over to Simon to kick us off.
Cool. Thank you very much for the intro. So I've got a sore throat today, so excuse me if I keep swallowing. But so I'm going to talk about graph queries with Postgres, and that also is the same thing as recursive queries. Okay, so I'm going to go into some detail about how to write the SQL statements and how to optimize them and various other details. So if you've got questions during this, then please feel free to speak up and I'll try to monitor the chat to see what's going on. Okay, so the starting point then is what is a graph? Well, a graph is a data structure that consists of nodes, which are just data items, and we have things called edges that connect the nodes. So graph thinking is really a different way of thinking about data from the relational model, where you tend to treat every single thing as identical and fitted within a particular schema. In a graph model, you can invent new relationships fairly easily and new properties on nodes fairly easily as well. So it is a slightly more flexible way of thinking, but actually also it can allow you to drown in complexity. But there's some dangers. So so there's some pluses and minuses about using the sort of graph style thinking about things. But why should Postgres users care? Well, mixed models are pretty common, and in the real world there are lots of examples of data models where trees or networks or graphs come straight out of the data. Obviously in the internet age, hypertext and social media are probably the two biggest new sources of graph style data. But also there's been a lot of success using graph style analysis for sort of criminal and fraud investigations. So is graph style thinking the right thing for every single application? Well, in a lot of cases, no. There are actually some specialized routing packages available. So if you're doing GIS style routing, then you might want to use the PG routing tool. So that might be the best approach. So what I'm going to talk about here is really sort of generalized graph data query writing. But it is relevant to Postgres. So let's start with a very simple graph. Obviously, as you can see, it's very, very simple. We've just got 5 nodes and a couple of edges. And I'm going to describe how to write queries against this data model. But I'm going to write the queries in a generalized form as if I was writing against a database that's got like 10 million rows in or something. So just to sort of give you a feel, we're not going to make any cheats based on knowing that that's actually a simple graph. But I use that simple data as a way of just explaining what's going on. So if we want to put a graph inside a relational database, then obviously it's fairly straightforward to do that. We can have a table called nodes, and each node has one row in the nodes table, and it's identified by a node ID. And then there's another table called edges, and each edge is represented once in that table, and it links two different nodes. Now, in that particular model, you're only allowed one edge linking two nodes, but in a generalized graph, you might have multiple edges between nodes. And in order to write SQL to traverse that graph, we generally might write that as a simple join. Now, if you look at textbooks that explain about graph thinking, they will show you this query and go, gosh, this way of writing SQL is just so awful, because you have to write an SQL statement and then you have to execute it multiple times. And each execution of the SQL iterates once through the graph. And obviously that is horribly inelegant. And I've seen multiple books explain that relational databases can't do graphs because this is ugly, okay? And it definitely seems inelegant. And so maybe we need a query language other than SQL in order to express graph databases and graph queries. Well, there are a lot of specialist graph databases out there. Neo4j, TigerGraph, OrangoDB are all different database products that specialize in graphs, and they have all released their own separate incompatible languages to allow you to express graph queries. Now, why have they done that? And that's because there's a lot of business problems that you can express in graph, but expressing them simply is really quite difficult. And so what people have tried to do is come up with a way of expressing graph problems more simply than would be possible in SQL. I'll come back to that. And so people have invented languages like Sparkle or GQL, but a proof a couple of years ago was that there's absolutely nothing in the language Sparkle that can't actually already be expressed in SQL. And so it doesn't really offer anything other than what you might call syntactic sugar as a way of expressing things. And actually, as we might see later, there are some concepts that you can't express in the Cypher language that you can express in SQL, for example. So it's actually a misconception that you need another query language and that you can't use SQL. So at this point, you might be confused. You might be saying, well, hang on, Simon, you just said this piece of SQL was inelegant, and now you're telling me that actually you can express graph queries using SQL. And that's because there's something that probably you don't know, and that is that recursive queries can be expressed in SQL. Now, the first attempts to do this were by Oracle 30 years ago, using connect by prior, and some of you may have used that particular syntax. But the SQL Standard itself, for the last 22 years, has had with recursive syntax available, all the way from SQL 1999. And it's been in the standard ever since. So for the last 22 years, you've been able to express graph queries in SQL. And that fact is not mentioned in any book I've ever read on graph queries. I wonder why. Anyway, so it turns out that Postgres has supported this syntax for recursive queries since 2009. So for the last 12 years, you've been able to write graph queries in SQL, in PostgreSQL, and yet no one ever tells you that. No one expresses whether that's possible or not. So really what I want to do in this presentation today is explain to you what's possible, how to do it, and explain how to do that with high performance queries. So an example SQL query that allows a recursive search of a graph is this. We use the keywords with recursive to begin expressing the details of the search. Now that one piece of SQL is all you need to search a graph of infinite size and complexity. Okay, that is all you need, one SQL statement. So if we go back to that earlier thought about, oh, SQL doesn't work because you have to express it like that, it's just simply that the people that wrote those things were expressing their poor knowledge of SQL that apparently goes back about 25 years. Because if they'd have been using modern SQL sometime in the last 22 years, then they would know about with recursive. So what I'm going to do is I'm going to break down this query into small pieces so that I can explain how it works and show you how it executes. So let's start off by making another simplification, which is I'm going to take the same picture of the graph expressed in the top right-hand diagram, and I'm actually going to have just one table, and I'm going to call that graph. So instead of having two tables, one for nodes and one for edges, I'm just going to have one table called graph, where each row in this table is one node, and all of the connections between nodes, the edges, are expressed as an array of integers. And those integers obviously hold references through to the nodes. So we're using the same node ID to connect the edges to the nodes. And the data in our table then looks like the query at the bottom right-hand side, where I say select star from graph, order by node, and you can see that node 1 connects to an array, and therefore it connects to node 2, node 3, and node 4, which is exactly what we have in the diagram above. Nodes 2 and 3 don't go anywhere, but node 4 connects to node 5, and node 5 doesn't go anywhere either. Okay, so you can see that I can express that graph much more simply using PostgreSQL arrays. And by using Postgres intelligently, we can express graphs much more easily than you might do using just what I might call a bland or straightforward relational model. So it uses a single table. It denormalizes the edges into an array of integers. And you can have foreign keys on this if you want, but of course they're optional. And in many ways, it simplifies indexes, simplifies queries, and it's possible to add additional information into the graph as well. Let me just continue with this graph. So I'm going to use this graph now to write a number of different queries. So the basic recursive query looks like this. We say with recursive, and then we define search graph. Now, search graph is not a reserved term. It's just the name of the subquery that we're writing. So there's a query term here that begins search graph as bracket, and that matches the bottom bracket here. So everything between those two brackets is the definition of the search graph subgraph. And the first thing that we do in a recursive query is we define the initial data, or what we call the non-recursive term. So this part of the query only ever gets executed once, okay? And this defines where we're starting. So in our query here, we're saying we're going to start at node 1. Now, obviously, you don't need to start at any particular place, but if you look at the diagram, it makes sense that I start at node 1 because that's how I've drawn the diagram. Obviously, we could have drawn that diagram slightly differently and started at a different node, but I've set things up specifically to start at node 1. If we wanted to start at a different node, this where it says where node equals 1, obviously that might be different. It might say where start with all of the people wearing a red jumper, okay? And then it would have a sort of variable number of inputs. But in this case, we're starting at one particular node in our data graph. The next thing that we do is we define the recursive term. And this part of the query gets executed multiple times, okay? And so in this term, you'll note that there's a join between a data table, which is graph, and obviously that's the thing that I said we were searching, so you should be expecting that. And we're also including the search graph. So you can see that search graph term is the same name as the with recursive term. And that's what makes it recursive. We're actually referring to itself so that the definition then becomes recursive. Now, this little diagram here, the sort of circular arrow is illustrating the point that we will take that part of the query and we will execute it multiple times, and we will keep executing it until we run out of things to process, okay? Now, I'll explain more about that in a sec, but the key aspect of this really is that there is a join between search graph and graph, and that is expressed in the one red line where we're saying link the search graph edges back into the node table in order to look up the next lot of nodes. And so by doing this, we're able to move iteratively using the recursive term to search further and further inside the recursive query. Okay, so that's the non-recursive term at the top, the recursive term at the bottom that contains a join back to itself to allow you to search the data. And that's it, basically. Those are the basics of the recursive query in SQL. But then, obviously, as is always the case, there's various other considerations that you need to think about. So using that basic query, we then need to consider what type of query results did you want? Because obviously, if your plan was to record all of the paths between all of the nodes, that is a huge result set, okay? And that's, if you think about it, that's like joining two tables without specifying a join condition or without any other form of where clause. So it's going to return lots and lots of rows potentially, and so you probably don't want that. So the question is, what do you want to see? And this is where we say we need to put in where clauses to control what happens. So we need to add a where clause to filter the results, okay? And so the way that we would do that is we get the starting condition in the non-recursive term by saying where node equals 1, and at the bottom we would put the ending condition, which is where search graph dot node equals 5, say, and that would search starting at 1 until we get to 5, okay? So by adding where clauses, it significantly filters down the actual search that is going to be executed. And obviously, that's going to reduce the amount of work we need to do to search the graph. And this is really the key difference between what you might call graph analytics queries and graph OLTP. Okay. And so just as in normal SQL, where some queries are short and return a small number of rows, then you also get analytics queries that potentially run for a long time and process a lot of data. Okay, so you need to be clear about what's actually happening in your recursive query. And one of the mistakes people make when they experiment with this is they write a query and then it executes for 5 hours and then think, well, it must be rubbish at doing graph queries. No, it's not. It's just that you wrote the wrong query. Okay, so you also need to decide what you want to see in terms of paths and the output. So if you're writing a query that has the shortest path between two nodes, then actually that is a very quick query to execute, because what it will do is that at any stage of the query, it will return just one row, which is the newest, shortest path. And that shortest path will make its way searching through the graph until it finds the end node. Okay, so a shortest path query can execute extremely quickly on Postgres. Obviously, if you're asking it to process a very, what we might call bushy graph, where each node is connected to, say, 10 or more other nodes, then you can see that a very deep query could potentially process many millions of nodes in its search. And really the key aspect of this is to make sure that we remove as much data as we can, as early as we can in the query. So in terms of the way that you would tune a graph query, it's exactly the same as you would tune a normal SQL query. Basically, filter out the data that you don't want as early as possible and make sure that that query is doing as little as possible in order to return you a correct answer. Okay, so the same rules apply to graph queries as they do to normal queries. Now, there are some other aspects specific to graphs, and that is that graphs can actually have loops in them, where the data takes you from one node to another node to another node to another node, and then back to the first one again. And that's what we call a cycle. And if you have cycles in your data, then the query could potentially continue forever unless you put in something to prevent that. So one warning there is if you say, oh, but my data doesn't contain any cycles, well, it might not now, and it might not in your test data, but if somebody inserts some data that's got a cycle into it, into the actual data in your production database, then your queries would suddenly start executing forever, which is not a good place to be, quite clearly. So one thing I would recommend is perhaps thinking about putting a statement timeout when you're using a graph query. But certainly in your testing, I'd make sure that you put test data that contains cycles so that you can actually test your SQL. So the way that we prevent cycles in a query is fairly straightforward, and all I've done is just add that line to the query. And what that says is we're going to keep track of all of the places that we have visited in the current graph. And then we're going to say, if you do a join and you come across a node that we've already traversed, then just exclude it from the result set. Okay. Now, adding that makes it doesn't really add significant more complexity the graph query, but it does significantly reduce the data that's processed, and therefore you will get an answer much faster, just simply because you're reducing the amount of work that you're doing while processing. So another common question that we have is, how can you tell what the depth of search is, or how many levels of search there are? And it's, as you can see, again, a fairly simple thing to add a level variable in there. Every time we go round the recursive term, we will add 1 to that level. So you can actually see how many hops it is between data items on your graph. So there's a couple of fairly simple things that you can add to your SQL to answer common problems. But there's another thought as well, which can occur, which in some data models, it's possible to have multiple paths between the nodes. And in this case, that causes a little bit of extra complexity, because you need to add a term into your query in order to get that to remove the multiple paths. So as it's searching, what you then need to do is remove cycles and remove multiple paths. Now, there's another way of doing this, actually, which is to use a group by and a summation. So what this option does is simply to sort the data and to pick the shortest path out of the multiple paths. And if there's multiple paths of the same level, then it will just pick the first one. So that's fairly straightforward, and it's very effective in reducing the runtime of queries that contain this type of data. Okay, so what I'm showing you here is that the SQL query in its basic form is fairly straightforward, and that we can add all these extra terms to allow us to deal with real world data and real world graphs that can sometimes contain sort of strange complexities. So the next thing to look at is an explain of these queries. And if we do an explain with costs off option set, then you can actually see how this executes. The CTE search graph is shown, and the node name is a recursive union, and that has 2 parts. The first part is the non-recursive term that gets executed once, and then the next term is a recursive part of the query, and this will get executed multiple times. And the way it works is we join the work table, which starts off as the non-recursive term, and we join that to the data, and then the output of this gets put back into a new work table, and then we will just run that again. So we keep executing against the work table until there are no rows left to process. Okay, so that's what an explain looks like. But most importantly, you can see that there's nothing about Postgres that's preventing you from using indexes in this type of query. And as a result, I can tell you that tightly written graph queries do execute very efficiently on PostgreSQL, so typically in a small number of milliseconds. So a larger example of a query written for Postgres, again using the array syntax and the array model, and including all of the aspects that I've discussed so far, gives you that as a realistic query. Obviously, if you want to put where clauses on there for various other search terms, then the query would get slightly larger, but that's pretty normal, isn't it, for a search? So if you're thinking, well, my queries generally look a lot more simple than this, well, a graph query is an advanced type of search. So if you were using a full text system, or you were using a GIS search, all of those types of query have much more complex search patterns. They complicate the SQL, and that's what we're seeing here. So it's no particular surprise that happens. So let me start to answer a couple of things. So will there be a playback recording of this? Yes, you will be able to access the playback. Could you post the create table query? Yes, it will be in the slides. I'll come back to stored procedures in a minute. Can you have a recursive query that goes from the bottom up, that is start at node 5 and end at node 1? Yes. I mean, a graph doesn't have a sort of top and a bottom. It's just the way I drew it. Okay, we could turn that diagram back the other way, and node 5 would be at the top, and so it's easy to start wherever you like in the graph and stop wherever you like in the graph. Okay, and as somebody points out, in that particular example I had, yes, there is no difference between rows 5 and 6. That was the point of that part of the example. Okay, you can see that those two rows are identical, and that's what's causing the multiple paths. So I'm showing this as a data problem for you to solve in your queries, because otherwise you might say, oh, well, it can't work because SQL can't cope with multiple paths. Well, it can. So it isn't necessarily the right way to model your data, but I'm just saying, if your data looked like that, we can still solve it. Okay. Okay, so I'll just carry on with some things, and we'll come back to performance in a sec, because I've got some other things to tell you about. So if we look at the SQL explain analyze for this situation, then you'll see that we end up with a fairly complex explain. So at the top you can see recursive union, and then you can see below that it's got two different terms. So the first term is an index only scan, and that's the non-recursive term, and then we've got a subquery scan on the rest of the definition. Now, if you look down the query to where we see work table scan, this, for me, is the key point of the query for a recursive query, because this is where we find out whether the estimated number of rows is similar to the actual number of rows in this particular execution. Now here you can see that Postgres thinks that there's going to be 8,750 rows, but actually there's going to be 55 rows. Now this number here, 8,750, is the total number of rows that get processed by all iterations. So this isn't per iteration, this is the total. So what it's saying is, I think when I execute this query from beginning to end with a variable number of iterations, I will end up processing 8,750 rows from the work table. But when we actually execute it, we see that the number of rows was 55. Now, one reason for that is that the number of loops in the actual execution was 4. And the Postgres optimizer currently assumes that the number of times that you will iterate in the query is 10 times. Okay. And unfortunately, at this point in time, there's no way to derive statistics for that. So it just simply estimates 10 every time, which isn't very useful that it's hard coded. And I would like to try and change that in the future. And the other thing it does is it assumes that the size of the work table each time through the loop will be 10 times the size of the initial search term. And so in this case, we end up with a much higher estimate of the work table size than it actually is. And what that then means is that Postgres thinks, oh, well, the work table is going to be massive, so I need to optimize other parts of the query to get that to work correctly. So based on its knowledge at the time, it ends up executing something that takes 1,775 milliseconds, so nearly 2 seconds to process that. Now, in this particular example, I have got 100,000 rows in that table. You can see when it processes the hash that it ends up with, it's 1 million rows in the table, not 100,000. So it's actually quite a big table, and that's why it would scan through that and take 2 seconds to execute. Now, if we are able to nudge the optimizer in various ways, we can get that to change plan. And so if we give it a little nudge, we can actually reduce the estimate of the work table scan, and then the plan changes suddenly, and we get execution in 17 milliseconds. So it's 100 times faster, okay? And obviously that's quite an impressive achievement, but all we've done is instruct the optimizer to take a different plan. Now, there's a couple of ways you can do that. You can change the cost of random page cost, or you can simply turn off SQL scans. That works. But what I've done is I've submitted a patch to Postgres core to allow you to change the estimate directly. So instead of using this hard-coded value of 10, it will allow you to set that to something more realistic for your particular query. Now, in that example, I set that to an estimate of a multiplier of 1 for the query rather than 10. And you can see the number of rows in the table estimate has gone down by a factor of 10. And as a result, that's caused it to change the plan, and that's why it's significantly faster. Okay. Now, is it the case that all queries are initially slow when you write recursive queries? No. In this particular example, I had to write a query against a table that had 1 million rows in it, and I had to get it to do 4 iterations through a search graph before I found a query that was slow enough that needed tuning. So if you are searching through data and you're only doing a fairly small number of iterations, or your data isn't particularly well connected, then you won't need to do these things in order to tune it. So Samuel's asking, could you show us the actual nudged query? The query itself is not any different. The only thing I did was set the optimizer parameters. Right, okay, so yeah, look, you know, I don't want to sort of jump into horrible complexities about graph algorithms, but the point I'm trying to make here is that you can search a graph in SQL, you know, in a Postgres database. You can write perfectly performing SQL queries in order to exercise your graph databases. Okay, and so there's lots of ways of doing it. So let's look at some comparisons of performance between Postgres and other systems. So in order to facilitate graph query benchmarks, there's a group called the Linked Data Benchmark Council, or LDBC, And I've been somewhat involved in that, just on the edge, really, not full-time involved. But it's a very carefully designed benchmark that allows people to compare different graph databases, and it's based around the concept of a social network benchmark, or SNB, and all queries in that benchmark can be expressed in SQL. So again, we're emphasizing that SQL is a language that allows you to express graph queries in. It's just many people don't know that. And there's been a number of benchmarks performed on that, comparing Postgres against Neo4j, especially Community Edition. And one of the things I've found, if you look at some of those queries carefully, is that actually the SQL that I've been showing are actually LDBC benchmark queries. And I've been, by rewriting the queries, been able to make the LDBC benchmark on Postgres go 100 times faster. Okay, so one of the things that's really happened there is that the Postgres side of things needs to be a little better tuned. So the reality is that Postgres can handle graph queries very nicely. Other performance information. So there's a paper published by Alibaba Cloud that shows that they're able to get 12,000 TPS on a graph containing 5 billion nodes, and they were able to execute graph queries in 2.1 milliseconds per query against a database of that size. So it's a decent size database with very fast response. There's another benchmark by ArangoDB showing in their view that they are faster than Postgres, but the point is, if you look at the speed of Postgres in that, you'll see it's actually fairly fast. And another paper that was published in 2019, Database Performance Comparisons and Inspection of Fairness, and it says in the summary of that paper, moreover, we refute some stated issues about the bad performance of relational systems by using a PostgreSQL database for commonly used test scenarios. And that paper goes on to explain that Postgres is actually quite fast. So this is academic results, nothing sponsored by my employer or anybody associated with Postgres. This is just objective analysis of what happens. And there's various other papers that explain about Postgres performance. So Postgres has recently implemented some new features in Postgres 14 that allow you to write graph queries a little bit more easily. So the first of those is the term search, which allows you to do a breadth first or a depth first search of a graph. And the second option is the cycle. Now, it turns out that both of these were already possible. It just simply makes it somewhat easier to write the queries when they contain these terms. And so what I've done is I've rewritten the earlier query using the new Postgres 14 syntax, and you can see that it says cycle on the ID and edge columns, set a column called isCycle, and it's using path as the name of the variable. So I've actually used the same name of the variable as I already was in the query where I was eliminating cyclic paths. So I already wrote the query to do this, but this is some very specific SQL syntax. Can this be done equally efficiently where a new row exists for each related child node? It can be done fairly efficiently, yes. Can it be done exactly the same efficiency? Well, in that model that you're describing there as a denormalized, the difference between a denormalized and a normalized model is the number of rows. Okay, so by processing significantly fewer rows, you can actually make the query slightly faster, and that's why I chose to do it. But actually, it actually also makes the SQL slightly simpler so that it fits on the page. So there's no reason to say that you have to use the formulation of a graph as an array in the way that I have done in this webinar. You can also write queries without using the array syntax. So it's not specifically more difficult. Okay, right. So moving on from there, I think somebody earlier had a question about, can't you hide the complexity of graph queries inside stored procedures? Yes, you can. What you get with Postgres is you still get all of the other features that you get with Postgres. And so if you want to write recursive queries in your applications, you don't have to wait for your sort of object relational mapper to decide that it will support recursive queries, because it might not, and it might not work very efficiently. But what you can do is you can write the recursive SQL as a view and then just allow your ORM or your application to retrieve records from the view without actually knowing that it's a recursive view. Okay, and that's a very good way of hiding complexity. So you don't need every developer that accesses your graph to understand the details of graph searching SQL. You can just write it once, get it to perform efficiently, and then pop it in a view. Okay, so it couldn't really be any simpler to use. And yes, you can use that for a sort of various types of graph search. Postgres also can Postgres push predicates inside the view having graph queries? Yes. The Postgres rewriter and optimizer work perfectly normally with respect to graph. It's not doing anything weird or clever. It is doing always what it normally does, which is amalgamating things together. So there's no problem about pushing things inside graph queries. What are the main benefits of using graph queries in Postgres? Well, that's a very strange question, because what I'm trying to say is that Postgres can be used for graph queries. Okay, you don't need to take your data out of Postgres and put it into another graph database in order to write graph searches. Okay, so if your data is in Postgres already, then you can write SQL to access that graph. Or if you haven't decided where to put it yet, Postgres is a valid place where you can put queries. Now, people have also said, yeah, but have you compared it with other graph databases? Look, I don't have any doubt at all that those graph databases are extremely highly tuned for particular graph applications. But what Postgres is a general purpose application, and it allows you to, a general purpose database, and that allows you to bring together all of the different features of Postgres to build an application. You don't have to just be extremely good at one thing and then lack all of the features in other areas. So another example of a feature that you get with Postgres that you don't get elsewhere is that you can actually use recursive DML for updates, inserts, and deletes. And what this allows you to do, for example, is to search a graph and update all of the nodes that it touches as it's executing. Or you can use it to delete, for example, if someone dies, you could delete that person and delete all the people that they were linked to, say, or delete all of the links that people had to you. So there's some clever things that you can do with Postgres. Right, so what exactly is Postgres then? Well, it's a multi-model DBMS. Everything discussed can still work with any data type. You don't need to use arrays. You can use integers. You can use big ints. You can use UUIDs. It all still works. You can also use other things like text or URLs. You can use row types in your queries as well. And most especially, you can definitely use JSON searches in graph queries. Okay, so if you've got a JSON document, and inside the JSON document, it's got a link to another JSON document, then that is exactly what HTML and the World Wide Web is like. It's documents that point to other documents, and that type of data fits perfectly in Postgres, and you can write queries easily using all of that. The syntax of some of those things differs quite a lot, because when you're accessing JSON fields, the operators slightly change. So this is a 1-hour webinar. Obviously, I could write all of these same queries about 6 different ways as a way of explaining things to people. But the main point is, that you're able to do things lots of different ways, and that's the key thing that you get with Postgres. So what's changing in the future? Well, the SQL Standard is going to have graph added to it. Now you might say, this is strange, but they're the SQL committee. Why would they add graph? Well, the thing is, they're not the SQL committee. They're the Data Access Standard Committee, okay? And so what the Data Access Standard Committee do is produce standard languages that allow people to access data. And so they don't define themselves as, I am limited to SQL. They think about how access to data needs to happen. And so what they've done is they've looked at various proposals, and there's a simplification of graph called a property graph query. And there's also a whole major new language called GQL, both of which are being studied for future inclusion within the SQL standard. Now, this was something that was supposed to come out in 2021, and I'm not sure of the exact details of that. I think it's just delayed rather than cancelled. But we're expecting to see that maybe in 2022. So basically, in the future, you're going to be able to write an SQL query that looks like this, and that is the outer bit looks like an SQL query, and then the inner bit has a match clause, which is normally the type of thing that you would see in graph languages. And what we're saying is that this query will work perfectly as a basic SQL query. Now, as soon as that syntax arrives within the SQL standard, then Postgres will start to implement that and to include within the basic product. So what I observe really is that there seems to be quite a poor market understanding of whether Postgres supports graph databases, and you'll see things like graph databases like whatever are best suited for graph data. And then somebody else commented a while back I do not see any support for graph database in Postgres 11. Now, the reason why we don't have support for graph database in Postgres is because we call it recursive query. Okay, so if you're looking for the term graph query, graph database, then you won't find it in the Postgres manual. Okay, but what I'm saying is that recursive queries can be used to search graph data, and it can be a very effective way of performing all of the things that you need to do with graph. Now, if you are an advocate of graph thinking within databases, then I'm sure that you have experience with a graph language, and you probably prefer not to use the SQL language. But that's not the same thing as telling people that SQL does not support graph queries. Okay, so if you look at Joe Kelko's book, Trees and Hierarchies in SQL for Smarties, it only vaguely mentions graph, and it doesn't go into enough detail to make it extremely clear, as I've done today, that actually you can write graph queries perfectly well within PostgreSQL. So unfortunately, Joe, don't buy that book because it doesn't give you the details that I've discussed here today. So Postgres, well, can one DBMS be the best at everything? No, it can't. It's very clear that special purpose databases can be better at Postgres, and that is in fact what Michael Stonebreaker observed probably 20 years ago, is that it's always possible to construct a database that is very highly optimized for one specific task. Okay, now, but if we have multiple contributors to Postgres who all have different use cases, then yes, PostgreSQL can slowly move towards supporting lots of different use cases. One DBMS can definitely provide the facilities for multiple additional features via extensibility. And that's definitely what we're seeing. And at the moment, there's an extension for Postgres called Agents Graph, and that's going through as an Apache incubator. I'm not sure where we are with that. I recently investigated it. It only supports Postgres 11, and there doesn't appear to be any support for later versions of that. So I guess if the SQL standard comes through and we see graph queries appear in standard SQL, then we'll be putting that directly into the Postgres project. So I don't think, there may be a short-term need for an extension, but in the longer term, this is something that will be in core. Okay. So I am required to tell you by my sponsors that what EDB does is supercharge Postgres. EDB sponsored Peter Eisentraut, who's the guy that spent time writing the new search and cycle clauses for Postgres, and I've done some work here to check whether things work correctly in Postgres, and they do. So the LDBC benchmark for Postgres is something that I'm going to submit changes to in the near future to speed up the execution. Not that we've done anything to Postgres, all I've done is rewrite the SQL correctly. Okay, so there were just some basic errors in the way that those queries were expressed, and we should be able to speed things up just by doing that. So EDB's contributed quite a lot to Postgres over a significant number of years, and EDB is going to continue to do that. So as soon as we see the graph query stuff appear in the SQL standard, then we'll begin implementing that, and then it'll be later version of PostgreSQL core. Okay, so there's quite a few contributors at EDB, and you can see Peter's on the core team there, does a lot of work on standards. So Peter and I have worked together on some of this stuff to analyze what's happening in graph queries. Anyway, so that's the end of that. EDB does support an advanced version of Postgres called EDB Postgres Advanced Server, but EDB does support core community PostgreSQL. Okay, so some people have said in the past that EDB only supports an advanced product, but actually a lot of the people and a lot of the customers use PostgreSQL open source edition perfectly happily, and everything I've told you today works with all of those editions. So this isn't something you need an additional add-on in order to get to work correctly. It works as part of the open source edition. Okay. Okay, so thank you very much for all of your questions. I've tried to answer some of the shorter ones, and obviously there's lots of different things going on about different thing. Yeah, so this there's a point being made about PG routing. PG routing is great and fast, but basically you have to pass the whole network to the extension, and beyond that it's quite hard to add stopping and other conditions to find the shortest path. And that is exactly the problem with graph databases. They are great and they're fast, but you have to pass the details of the network across to the other database in order to get it to work, and then you have to get the results back again. So if you're able to express the queries that you want inside the Postgres database, then actually that is probably the best way to do it. Okay, so I don't want to steer you away from PG routing, but it's actually one of the aspects of a specialized graph package is that it there are some downsides against the generalized way that you can use things with Postgres. So I've talked for an hour. Luckily enough, my throat hasn't given out, so that's a good thing. So I can say just thank you very much for all of your questions. I hope you've enjoyed what I had to say, and this will be recorded so that you can watch it again and maybe ask further questions as a result. So this is just a short webinar to illustrate the key points that you can express your graph queries in the SQL language, and they will run efficiently on PostgreSQL. Okay, so thank you very much for listening. Cheers.
Thank you so much, Simon, and thank you all for attending. We'll follow up with questions that were not answered, and have a wonderful day.
Okay, thank you very much, everybody. Bye now.